All right, and let's just take a look. We have some new things on MathBreeze, so we'll look over there first. So here are some announcements. Okay, this I think I had up yesterday. We have a new Readly assignment, just a few examples, and here I have two new multiple choice assignments on MathBreeze for 103 and 104. Okay, so take a look at that. That's for Monday. All right. So last time we were looking at alternating series, all right, in section 105, and we said the main theorem says that an alternating series, remember alternating series is of this form, like this, minus 1 to the n. It could start n equals 0 or n equal 1. All right, so this is an alternating series where these are positive. So basically it just alternates between positive and negative. The terms alternate. So that's an alternating series. And we have some special theorems about an alternating series. So the main one is if you want to prove that an alternating series like this one converges, you need two things. All right, the first one, to prove convergence, you need that, first of all, that the terms a to the n, the limit is 0. That's the first thing. And the second one is that they decrease. A to the n plus 1 would be less than or equal to a to the n. So the terms decrease. So these are the two things for proving convergence. The first one's usually the easier one, the limit. The second one, showing that they decrease in this way, the one tool that we have is looking at the corresponding function and show that the derivative is negative. So that's what we'll do in these examples. All right, so here we have, we want to know, does this converge or diverge, and is it absolutely convergent? I think I need a little more room. I'm going to pull the other one down. Let me just move this one down. Okay. Okay, so we want to know, are these, we want to show this first, that a to the n goes to 0. Let's show that first. All right, so that's the first one. Let's say we want to show a to the n goes to 0. So look at the term without the, in absolute value. So we're looking at square root n over n plus 2. And we can just divide top and bottom by n. N is the largest power. All right, so that's usually what we do here. So let's just divide everything, numerator and denominator, by n. Okay, so here we get the numerator is 1 over square root n. All right, just multiply top and bottom by square root n, and that's what we get, 1 over square root n. And here we have 1 plus 2 over n. All right, so because this n ends up in the denominator here, okay, and here these go to 0. All right, 0 over 1 is the limit, so the whole thing is 0. The limit is 0. Oh, not that it equals to 0, it goes to 0. Let me write goes to 0. Okay, so I'm just going to write it like this. Goes to 0, and this is the limit as n goes to infinity. All right, so that's the first part. And now we want to show that the terms are decreasing in this way. So we're going to look at, all right, so this is the second thing we want to show, an plus 1 less than or equal to an. So we'll look at the function f of x, just replace n with x. And we want to show, is we want to know, is f prime less than 0 for x greater than 1? All right. It really could be something larger than 1 as well, but anyway, like I mentioned before, but let's do f prime. So we'll just have a quotient rule over here. Derivative of the numerator is 1 over 2 square root x minus the numerator times the derivative of the denominator. Now I'm going to multiply top and bottom by square root x. So here we have 1/2 multiplying by square root x here. These cancel. So we just have 1/2 x plus 2 minus x. Multiply this by square root x. And in the denominator we have square root x, x plus 2 squared. Okay, so up here we have 1/2 x plus 1 minus x, just multiplying the parentheses. All right, so we have minus 1/2 x plus 1 over that denominator. Okay, so this is always positive. The denominator is always positive. That's square root and this thing squared. And it's 0 when x is equal to -2, but we're only interested in values that are 1 and beyond, okay? 1 and greater. So let's just look at the numerator. We do a plus minus analysis, and we just have to put the 0 of the numerator there. All right, let me just factor out. We see that if we factor out the minus 1/2, here we have x minus 2. That'll give us, multiply back, that'll give us the plus 1 here. All right, so 2 and beyond. All right, but 2 and beyond, this thing is negative. All right, like I said, the denominator is always positive. Put in a value like 3, for example, and because of this minus 1/2 on the outside, we see this is negative. Now we said x greater than 1, but really it doesn't matter. As long as it's the tail end, it's fine. X greater than 2 is also is fine because you have the first term plus the rest. So for the rest, you have an alternating series that has terms decreasing. Okay, so that's okay. All right, in other words, you can break up the series like this. Our series started with, let me see, with 1. It started at n equal 1. So just take the first term and then the rest. So for the rest, we have for x greater than 2, and we have minus 1 to the n. Okay. So this alternating series, I think maybe it's, if n is 1, it starts off at minus, although this is n, starts at n plus 1. Yeah, n plus 1. So it's going to start off plus. Okay. All right, so the fact that it's decreasing, that we showed an plus 1 less than or equal to an for x greater than 2 is really good enough, because we can think of this series as the first term and then the one from 2 and on. So from 2 and on, we show it converges. All right, so obviously, if this is finite, this is just some finite number, the whole thing will converge. So you really don't have to show that f prime is negative for n greater than 1. All right, you could go beyond that. All right, as long as the first few terms aren't equal to infinity, which they don't. They're just finite numbers. Okay, so we did that one. We're also going to ask about, what about absolute convergence? All right, what do you think? By looking at this, what do you think it's absolutely convergent or not? What do you think? In other words, if we get rid of that minus 1 to the n plus 1. Okay, so Elizaveta asks, can x equal to a half? Well, really, what we just want to show that f prime is negative. That's all we want to show, that from some point on in the right-hand tail, f prime has to be negative. All right, so it is negative. Yeah, at x, maybe you're asking, can x equal 2? Anything that makes, as long as the denominator isn't 0, we're good here. All right, here the denominator is 0 and x is equal to -2. Okay, so that's not a problem, because we're only interested in x values that are greater than or equal to 1, right? Because our series starts off at n equal 1. All right, so we don't have, if we had here something like an x minus 2 in the denominator, we would have a problem. But so everything, the first few terms are, the first term is finite, so that's not a problem, and the rest, we're starting at 2 and beyond, so that's also okay. As long as the tail end is negative. It can even start at 100. It doesn't matter, as long if the first 100 terms don't have, are finite numbers, then this can even start at 100. It's no problem. All right, we were going to ask about if this is absolutely convergent. So let me move this down. Okay, I'll move it down some more. Okay. So we want to ask if this is absolutely convergent. So let's do that. Now you should have a little bit of a feeling for what's absolutely convergent, what isn't. So let me write this down. So this is the sum minus 1 n plus 1 square root of n over n plus 2, right? N plus 2. And then goes from 1 to infinity. So absolutely convergent, we want to know, does this converge? Square root of n over n plus 2. That's what absolutely convergent would mean, without the minus 1 to the n plus 1. All right, so just look at this. What could we compare this with? What would this, remember, we just want, we could compare this with, just take highest power on top, highest power on bottom. So we would compare this with the following series, n, square root n over n, which is equal to, multiply top and bottom by square root n, it's 1 over square root n. Does this converge or diverge? This one that I just circled. Someone want to tell me converge or diverge? That you should know just by looking at it. By the p-test. What is that? Right, that diverges by the p-test. Because this is equal to n to the 1/2. If the exponent is less than 1 in the denominator, it diverges. So this diverges. And that's what we're going to compare it with. All right. We can compare in a, I'm just thinking if we can do a direct comparison test, but that wouldn't, a direct comparison test wouldn't be appropriate here, because these terms are just a little bit, because of the plus 1, a little bit smaller. If these were bigger than this, we could do direct comparison, but because of the plus 1, these are a little bit smaller than this. If this were a minus 1 here, we could do the direct comparison. So we'll do a limit comparison. right, so we're comparing 1 over square root n to a ratio 1 over square root of n to our series. Okay, this is 1 over square root of n times n plus 1 over I'm just flipping this. That's n plus 1 over n, which is 1 plus 1 over n. And that goes to 1. And now I'm going to write limit n goes to infinity. All right, so it goes to some number L, which is greater than 0. All right, so by the limit comparison, that means that our two series since this one diverges, they both diverge. So in other words, if the L is greater than 0, that means whatever this one does, this one will do as well. So we already know that this one diverges. So that means this one also must diverge. So they do the same thing. If the limit comparison is some number greater than 0, that means they're the same in terms of converging or diverging. So that one diverges, so the first one diverges. All right, so that would mean not absolutely convergent. So that's what we conclude there. All right, let's look at the second one. Okay, I'm going to pull down number 3. I'll pull it down a little bit more. Okay. Okay, so here we want to know convergent or divergent, and then later absolutely. So first convergent or divergent. All right, so first we want to show a to the n goes to 0, which it does right away, because the denominator is going to infinity. All right, so we're taking the limit as n goes to infinity. So that goes to 0. And now we want to show an plus 1 less than or equal, greater than or equal to, less than or equal to a to the n, that the terms are going down. All right, so that's what our main technique will be looking at f of x and writing the corresponding. Since ln x is always increasing, it has to be true. All right, ln x is always increasing. You could do it really, if you want, you could do it that way as well. You could say, let me just write in parentheses, if we put g of x equal to ln x, we know ln x is always increasing, so monotonically increasing. In other words, ln x2 greater than ln x1 when x2 is greater than x1. Okay, that means it's monotonically increasing, not even a greater than or equal to. We have a greater than there for x2 greater than x1. So if the denominator is always increasing like that, then 1 divided by the denominator is always going to be decreasing, monotonically decreasing, which is what we want to show. So you could really show that the denominator is increasing in this case. I'm just doing it in parentheses because that's not usually what we do. But let me just show you. All right, so here it's very easy. G prime is this. Okay. And that's greater than 0. We're talking about x greater than 2. 1 over x is greater than 0. So that means it is increasing. Okay, so if that's always increasing, then 1 over ln x must be decreasing. All right, but that's just on the side. That's not what we usually do. Usually we show more directly that this is negative for x greater than 2. So f prime of x. Okay, so take the derivative. This is, I'll take the derivative just by the power rule. Okay, we are going to get something negative. Okay, so this is negative for x greater than 2. Okay, the denominator is positive for x greater than 2, the numerator is minus 1, so this is negative. All right, so we're done with an plus 1 less than or equal to an. So the terms are decreasing. All right, so showing both those things, we have convergence. I think it went from 2 to infinity, so this converges. Now absolute convergence, I have to move this down again. What do you think? Do you think it converges absolutely 1 over ln n? What would you guess? Like I said, you have to develop a feeling for these things. In other words, you should know the answer ahead of time, all right, and then figure out how to prove the result. Okay, so so now we're looking at absolute convergence. All right, we're looking at sum 1 over ln n. Okay. Well, if you think about, like I said, you have to have some reference points. We know that sum 1 over n diverges. That we should know by the p-test. So if we look at x and compare it to the graph of ln x, okay, this is y equal x. This is y equal ln x. Y equal ln x goes to infinity more slowly than y equal x. So that's basically, and we know that this thing by the p-test that diverges. All right, so we expect this one to diverge as well. Okay, so we expect this to diverge because the denominator is getting bigger more slowly. It's going to infinity even more slowly than this one. It's only when the denominator goes to 0 very quickly that we have convergence. All right, here it's going to 0 very, very slowly. So just from this picture over here, we're expecting divergence. All right. Now the problem here for absolute convergence, how do we show that this converges absolutely? So you have to, it's not immediately obvious in terms, it's hard to do an integral test because we don't know how to integrate 1 over ln n. All right. If we just did an integral test and showed convergence, that would be easy. So this one, this is hard to integrate. We don't have a method for this. All right. Okay, but look at this series. We can do a direct comparison with the following. Let me just write compare. Compare this one compare it to this, and let's say we do a direct comparison, not a limit comparison. Well, because of this n in the denominator that's missing in this denominator, okay, these denominators are bigger. All right, so this is going to be smaller. These are actually bigger than this. This has a larger denominator than this one. So this fraction is definitely smaller than this one. So if this thing diverges by direct comparison, so will this. Okay. So what we want to do is we want to show, this is what we want to do. We want to show that this one diverges. And the only reason why I'm choosing this one, where I'm choosing this as a direct comparison, is because this one we can easily integrate. Show that that diverges, and that'll imply that that one diverges because of this inequality. Okay, because these are even smaller. So if this one goes to infinity and it's even smaller, that one will definitely go to infinity. Okay, we expect it to go to infinity. This denominator gets big very, very slowly, like we said over here. So we expect this to diverge. All right, well, okay, so we're going to show that this one diverges by integral tests, because it's easy to integrate. All right, so let's do that. That's the only reason why we chose that. Okay, let's remember how to integrate this. Put the 1 over x on top and put the ln x on the bottom. And this is what we call the log integral in Math 16. This is exactly of the form f of x on the bottom, f prime of x on top. So this is equal to the log of the denominator, which comes out to log x. And now we're integrating from 2 to infinity. All right, so usually what we do is we put an r here, and the limit is r goes to infinity. So we'll do that. So let's do limit r goes to infinity. All right, so the main point is this goes to infinity. Since ln r goes to infinity, the ln of infinity is infinity. Think of that. Think of it like that. That piece goes to infinity, so diverges. So the conclusion is, like we thought, not absolutely convergent. But like I said from the beginning, you should really have a feeling for this, because you should realize from the graph of ln x, it goes to 0 very, very slowly. It goes to infinity very slowly. The only things that converge of the form 1 over an expression is if the denominator goes to 0 quickly. Sorry, goes to infinity quickly, like something like n squared is fast enough, or n cubed, we know by the p-test. But ln n is very slow. All right, we know that from the graph. So we expected it to diverge. Okay. Let's go to the last type of problem that we had in this section, where we were approximating the sum within a certain amount. All right, so in this case we chose 0.01. All right, well, the approximation, the error term, so we want 0.01 to be the error of our approximation. All right. So what we saw in what we saw yesterday is that the error is less than the first term that's left out. Okay, so all we have to do is look at the various terms in absolute value until we get to a term that's less than 0.01. So we'll just calculate some of these. Okay. Let's write these out. Let's write out a few of them. So n is starting at 0, so this is going to start at a positive value. So first we start for n equals 0, we have 1 over 1 factorial, then negative 1 over, now n is 1, so here we have 3 factorial. Okay, it's starting to alternate. This is n equal 0, 1, now 2, 4 plus 1, so we have 5 factorial. So you see we just have these odd numbers. Okay, now minus 1 over, it'll be the next odd number, plus 1 over the next odd number. All right. So let's just find one that's less than 0.01. I'll start with this one. 1 over 3 factorial is equal to 1 over 3 times 2. 1/6. Okay, that's 1/6 is not small enough. Okay, 1/6 is 0.166. Okay, we're looking for something less than 0.01. So let's try 1 over 5 factorial. 5, 4, 3, 2. Okay, 20 times 3 is 60 times 2 is 120. Okay, so that looks good. That's equal to 0.0083. Okay, so this one's good. All right, so we can approximate by just looking at the first two terms. This is our approximation. That's all we need. All right, so our approximation is 1 minus 1 over 3 factorial, those first two terms, plus or minus the error. We'll round it off to that. All right, so that's 1 minus 3 factorial. That's 1 minus 1 over 3 factorial. Okay, just 1 minus, let's do 0.166. All right, so I'll do that. Okay, so our approximation is 0.833 plus or minus. So this is our approximation. Okay. So in order to approximate this entire sum, we got a pretty accurate approximation just from the first two terms. The rest are that small. The sum of the rest is less than 0.01, so we can get a nice approximation just by those two terms. That's how quickly these die out. The whole infinite sum, starting at the third term and on, was less than 0.01. All right, so that's how we approximate, and only for an alternating series. All right, for a non-alternating series, we don't have this type of approximation. This is only for alternating series. Okay. All right, so let's go on to another test. So we're going to look at, first of all, any questions? All right, let's go on. We're going to look at another test, 106. It's called the ratio test. Okay. Okay, so here's the main theorem in the ratio test. So here's what we have. This sum a sub n is a series with terms that are greater than or equal to 0. Okay, so we say that this converges if the following is true. The limit as n goes to infinity of an plus 1 over an is less than 1. Okay. Now, I'm surprised at this condition, and I'm going to look it up. I just want to make sure that that's true. I don't understand why you need that. So let me just look up to make sure I wrote that correctly. Ratio test. Oh, okay. Sorry. It's with non-zero terms, not greater than. Right. You could have negative terms. It's non-zero terms. All right. That makes a big difference. So they could be negative. Okay. They could be negative. So this thing converges is the limit of one term, a term divided by the one before it is less than 1. All right. So that's the ratio test. This is the main part of the theorem. All right. And then we have a couple of other parts. It diverges if the opposite is true. If you have this. Okay. And if you get 1, then it could converge or diverge. It's inconclusive. Okay. So that's the ratio test. And basically, what this is saying is that you know that a series converges. You know how a geometric series converges. A geometric series converges if the ratio of one term to the term before it is r, where r is less than 1. So for geometric series, you have an exact ratio between a term divided by the term before. You have an exact ratio of r. So this one is sort of like an approximate geometric series. If a term divided by the term before it is always less than 1, all right, or as n goes to infinity, it'll always be less than 1, then it's similar to a geometric series. All right, so that's what's going on here. Here you have a series that's sort of like, you can think of it as an approximate geometric series or similar to a geometric series. All right, so I'll just write that in a note. All right, so for a geometric series, a to the n plus 1 divided by, for let's say a convergent geometric series, is going to be equal to r, which is less than 1. Okay, so here, for n big enough, let's say greater than, some capital N, in other words, down the line somewhere, we have a to the n plus 1 divided by a to the n, okay, less than some r, which is less than 1. So that's what's going on here. Essentially, it works in a similar way to a geometric series. Now you understand this? All right. So the proof really just compares the series to a geometric series. It just does a direct comparison to show convergence with a geometric series with ratio capital R, where the ratio is less than capital R. All right. So so that's the basic idea here, is that this is similar to a geometric series. Okay, so let's look at an example. I want to start with an easy example, so I'm just thinking about one that, this is not from the book, so I hope this will be easy to show. Just one that I'm making up. Okay, I'm making it up on the spot. Okay. All right, let's look at this one. Now, we want to know if this converges using a ratio test. We can actually show that this converges using an integration test, using the integral test. It's not hard to show this converges. So we want to know converge or diverge, but we want to use the ratio test. Okay, now when n goes to infinity, the denominator is increasing very, very quickly. I'm just giving you a feeling for what's going on. The denominator is increasing very quickly. The numerator is also increasing, but not so quickly. Not as quickly. It's lagging behind. If we didn't have this numerator, if we had a 1 over here, this would be a geometric series. So I'm choosing this series because it's close to a geometric series. All right, it's close to 1 over 2 to the n. For large n, for n very large, this is going to be insignificant compared to this denominator, which is huge. This is going to lag behind a lot. So this will be similar to 1 over 2 to the n. Okay, so let's try the ratio test on this. All right, so what we're going to do is a to the n plus 1, just divide. Here everything is positive, so the terms here are positive. All right, so n plus 1 would be this. And that's the denominator. All right, so let's just flip that. I'm just going to flip the denominator. All right. Okay, let's turn this around a little bit. Let's just put the n plus 1 over n on one side, and here in another fraction put 2 to the n over 2 to the n plus 1. Okay, so this is equal to, I'm going to divide over here 1 plus 1 over n. That's for that first factor. And the second factor is just 1/2. Okay. And now we're ready to take the limit as n goes to infinity. All right, so this goes to 0. All right, so we see the whole thing goes to 1/2, which is less than 1. So that means it converges by the ratio test. So what the ratio test is showing that for this particular series, the ratio of one term to the one before it is close to 1/2 as n goes to infinity. All right, so this doesn't, even though you have this n over here, it's still the ratio of one to the next is close to 1/2 as n goes to infinity. So that's what I meant by this series really is similar to a geometric series. All right, if it weren't for the n on top, it would be a geometric series. So I like this as a first example because you can sort of understand what the ratio test is doing. All right, let's look at another one. Okay. Okay, here's another one. Okay, this one's from the book. Here we have 2 to the n plus 1 here. And here we have 3 to the n. Notice we could just you don't have to do this, all right, but you could factor out a 2. If we factor out a 2, we have, I'll just leave the n squared there. Then we have 2 to the n over 3 to the n. We have 2/3 to the n. All right, now I would say this is similar to the geometric series sum 2/3 to the n. I don't think this n squared is going to interfere a lot when n's going to infinity. But let's check it out, okay? All right, so we're going to do, I'm not using absolute value because everything here is positive. Okay, add 1. Here we have n plus 2. So this is the top term. And the bottom one. Okay, now we're just going to flip the bottom. Okay, just flip the denominator. Okay, now start rearranging things. All right, let's put the 3's on top of one another. Let's say 3 to the n over 3 to the n plus 1. Okay, let's put the 2's on top of one another. Here we have 2 to the n plus 2. And here we have 2 to the n plus 1. I'm looking at this. Okay. And then the n's. Okay, so what do we get? Well, this is 1/3. This is 2 over 1. All right, so we have a 2/3 over here. And over here we have n squared plus 2n plus 1 over n squared. Okay, so what does this go to? Okay, here I'm just going to keep writing 2/3 here. And here just divide, so we have 1, divide by n squared, 1 plus 2 over n plus 1 over n squared. All right, so now we're ready to take, actually this previous one was just an equal sign. This was still an equal sign, no limit yet. Now I'm drawing an arrow because now we're ready to take limit n goes to infinity. And we get 2/3. Okay, so you see this, these two go to 0. All right, so we got 2/3, which is less than 1. So that means converges by ratio tests. All right, so that's a typical problem. So you see what this rearranging here is typically what we do to simplify. Divide whatever you can easily divide, reduce, that is, reduce as much as you can, and that's it. All right, let's do one more example. This one's also from the book. Let me see what number this is. 3. This is n to the n over n factorial. What do you guess? Converge or diverge for this? If you look at, let me just, any guesses? Okay, let's think of, let's say n is equal to 5. So for n equal 5, what's our term? We have, this is our term. 5 multiplied out 5 times, and here we have 5, 4, 3, 2, 1. You see this? It's greater than 1. You see? The numerator is larger than the denominator, and that's true for all of these. The numerator is always larger than the denominator. These are definitely not going to 0. There's no way this is going to converge. All right, these terms the terms do not go to 0. All right, they're getting bigger. So there's no way it's going to converge. And we'll see that by the ratio test. You could just show the limit doesn't go to 0, and that's the end of the story. But let's do the ratio test, since that's what we're doing over here. Okay, n plus 1, that would be n plus 1 here to the n plus 1. Okay, and now we'll just flip the denominator. Okay, so let's keep going. Now I'll do the rearranging. So we can do some reducing. Let's do that. Okay, so that was the rearranging. So now we're ready to do some reducing. All right, so n plus 1 to the n plus 1, that's n plus 1 written out n times. Let's put this all in one fraction. These are both, this could be power n. Here, let me rewrite it. Sorry, let me do this in 2 steps. Okay, we can write it like this. This is okay. Now the second one, this is n times n minus 1 times n down, and this one is n plus 1 times n times n minus 1 and down. So all this, that all cancels. Okay. Okay, here, so this is n plus 1 over n. And here we just have n over n plus 1. We're left with that, n over n. We're just left with 1 over n plus 1. Okay, so those also cancel. So here's what we're left with. This is 1 plus 1 over n to the n. And now we're taking the limit as n goes to infinity. Okay. I'm pretty sure this goes to e. All right, so that's something that you could this is something, let's say we just remember that this is equal to e, which is greater than 1. So that shows divergence. Okay. To show that the limit is e, it takes a little bit of work, so I don't want to do that now, but I'll just show you what to do. Okay. If you want to show that that limit is equal to e, all right, what you have to do is you have to do the following. You put y equal to like that. This is what we did, I think, in Math 16, when you had some expression with x's here and x in the numerator, and you want to take the limit as x goes to infinity, you had to take the log of both sides just to bring that n down. Okay, and this is equal to, and then you use L'Hopital's rule. All right, so it's a little bit of work, so I'm just going to top and bottom go to limit, and we're doing limit as n goes to infinity. This goes to 0, Actually, this goes to 0. Let me just make sure. Limit n goes to infinity. This goes to 0. And this one goes to infinity. As n goes to infinity, sorry, we have ln 1. This goes to 0 as well. Ln 1 is 0. 0 is over 0, so you're going to use L'Hopital's rule. All right, so I'm going to write etc. here. You can finish this. Okay. And maybe we'll finish it next time. Okay, so I'll show you that. All right, I think I didn't anticipate that this would have this little punchline at the end where we had to do sort of one of the more complicated types of limits. All right, but so I'm just going to assume that you remember from the definition of E that this goes to E. I'm just going to assume that. All right, and E is greater than 1, so by the ratio test we have divergence. Now again, let me just say that you should have a feeling for this and realize that these terms are not going to 0, that the numerators are always bigger than the denominator. So it would be simpler really just to, here it's easier. We did the ratio test, but it's easier in this case. It's easier to show that just that an doesn't go to 0, but that an goes to infinity. Okay. And doesn't go to 0. So that would mean divergence. So that's really easier to show that. The terms have to go to 0, otherwise you don't have a chance of the infinite sum being finite. The terms have to die down very quickly, die down to 0 very quickly. So that would be easier here, easier than the ratio test. All right, so I think we're going to end here. You have homework to do, so do that homework, do the homework. I'm still grading the exams. Slowly I'm grading them, all right? So during the week I'll be grading the exams. It takes a long time with the emails, you know, to do. It's much easier when you have actual papers to grade, all right? It takes longer with the emails, with the email files. All right, so I'm still grading them. Any questions before we go? All right, so we'll just end here and see you tomorrow.